All right, so the lesson today is about carboxylic acid and ester. So these are two new functional groups that we'll be learning, and we'll be learning about their properties, their IUPAC nomenclature, so different naming rules for these guys, how they react, and how do you make these from other compounds. All right, so let me just bring you to this page. This one checks off all the functional groups that we have learned. So right now, today, we are going to focus on these two. Okay, as you can see, we're almost finished with the list. And after this, it will just be amine and amide. All right, so first off, carboxylic acids. You probably all had oranges, lemons, vinegar, or tomatoes some point during your lives. And all of these have something in common. They're all sour. Okay, and they're sour because they contain carboxylic acids. And you learned earlier that acids are indeed sour. As the name would suggest, carboxylic acids are acids. Okay, it has literally the word acid in it. We have learned a lot about acids in grade 10 and grade 11. However, we didn't really focus on organic acids, mostly the inorganic ones like HCl, like HBr or sulfuric acid, carbonic acid, all those. Organic acids all have a carboxyl group, okay, and these are called the carboxylic acids. A carboxyl group is denoted as R with COOH. This means that the carbon is double bonded to the oxygen, which is then single bonded to an OH. Okay, so the carbon is making 4 bonds. 3 of those are with oxygen and 1 other bond with a carbon chain. A little interesting story about carboxylic acids. Ants, a lot of species of ants and their larvae, they all have a vinegary taste because they produce methanoic acid. Okay, methanoic acid is almost like vinegar. The vinegar that we put on food is ethanoic acid with 2 carbons. Methanoic acid has 1 carbon, but still an acid. They make the acid because of self-defense. However, some cultures consider them to be delicious. I don't know why they don't have vinegar, but they decided to grab these ants. They pick out the large ones, so they're very juicy. They basically squeeze the ants on their salads to use as dressing. Okay, they didn't want to go to the convenience store to grab some vinegar, so this is the alternative. I don't find this palatable, but hey man, to each their own. You might enjoy this if you just try this out. So how do we name carboxylic acids? This is very similar to naming aldehyde, which we talked about last class. Well, you have to identify the longest chain, okay? And the longest chain must contain the carboxyl group. So this one has to be on carbon number 1. There's no way for the carboxyl group to be on any other carbons because the carbon will have a double bond O and then another single bond OH. That's already 3 bonds. So you're now only able to make 1 additional bond, and that has to be with another carbon as part of the chain. So you don't have another bond available to make another bond with carbon. This means that you have to be a terminal carbon. If you're a terminal carbon, of course you're always going to be carbon 1. All right, so you do not need to show me that this is on carbon 1 because it always has to be on carbon 1. So all you have to do is end your name with the suffix oic acid. All right, notice that there is a space between the oic and the acid. This is one of the few examples where a space can be had in your name. Okay, but all the other ones we've learned so far, no space. Of course, you will identify all the other substituents. So let's actually look at this example on the page. If you count the carbons, there's only really one way to count this. You go from right to left. The carboxyl group is obviously on carbon 1. So this is a 6-carbon carboxylic acid, and we just call this hexanoic acid. The hexa for 6, oic acid for the carboxyl. And then you bring your attention to the substituents. That's a 3-chloro. That would be a 4-methyl. So put this together alphabetically. You have 3-chloro 4-methyl hexanoic acid. All right, so note the space between the word hexanoic and acid. So this is fairly simple. That's it. There's no tricks to this. I'll give you some time to work on this example, 2 very simple example problems. I'll give you like a minute, and then I'll quickly take these up. All right, so I'm just gonna take this up. The first one is very simple. It has 2 carbons. It looks like it has 1 carbon, but you gotta realize that this actually has 2. If you have 2 carbon, you're ethane, and just slap on the oric acid, you would have ethanoic acid, and that's all you need. This is also known as acetic acid. Okay, they're literally the same thing. Ethanoic acid is the IUPAC name, that is the official name. Acetic acid is a common name because ethanoic acid has a lot of syllables, so acetic sounds better. And acetic also refers to 2 carbons. This also goes by another name. This is the vinegar that we eat. So people also call this vinegar. Vinegar is just a 5% solution, amongst other stuff, of acetic acid. Okay. The one under that, that's a little bit more difficult, but not by a lot. It has 4 carbons in the longest chain. So that will be a butanoic acid. But this one has a group that has a 3-methyl. Putting this together, simply 3-methyl butanoic acid. Okay, there are no tricks whatsoever. I hope you got both of these. This page, though, is substantially more difficult than the previous one, especially the one on top. Does anyone want to venture a guess as to what this is? There's a benzene with the COOH sticking out of the benzene. So what do you think the name of this is? It's exactly what you think it is. Anyone? Seriously, nobody wants to venture a guess? You have a benzene, and it has a carboxyl group, meaning that this is an acid. So the natural thing to name it would be just benzoic acid. All right, it's that simple. You're probably thinking that in your head, thinking that, well, it can't be that. Well, it is actually benzoic acid, okay? Nothing to do with phenol. I know benzene with an OH is phenol, but in this case, we're using the actual name for benzene, so benzoic acid. Please make sure that you know this is benzoic acid. If you don't know that and trying to name it anything else, you would get it wrong. The one on the bottom is actually fairly simple. It just has a lot of branches. But at this point, we've done so much naming. Having a lot of branches shouldn't be the difficult part. So you count the longest chain. You start here, you go 1, 2, 3, 4, 5, 6. The longest chain has 6 carbons. And this is an acid, so that would be hexanoic acid. And then you go for the substituents. You have a 5-fluoro, there is a 4-ethyl, and then there's 2,2-dimethyl. So putting everything together, so E before F before M, you would have 4-ethyl, 5-fluoro, 2,2-dimethyl, hexanoic acid. All right. Any questions regarding naming acids so far? All right, good. This one is difficult, okay? How would you name something with multiple functional groups? I kind of talked about this in the last lesson, which I guess you missed. But let me just reiterate right here. If you have multiple functional groups on the same compound, there is a list of hierarchies. Right? The functional groups are not all equal. Some of them are more important than others. And that list is posted right here. So according to that list, carboxylic acid is number 1. And then followed by amide and then aldehyde, but we don't have amide and aldehyde in here. We only have carboxylic acid, a ketone in the middle, and an alcohol to the left. All right, so having these 3, you compare their hierarchy. Carboxylic acid is number 1. That is the most important of them all. So the whole compound will be named after the carboxylic acid. Okay, you will name it as if this is just a carboxylic acid. The other functional groups, they're relegated to become simply branches. Okay, they lose their special status for naming. As a result, you will number it from the right side. You number from the right side because the functional group, the carboxylic acid, must have the smallest possible number. So the OH on carbon 5 is crying in the club because it's a lowly 5. Okay, if it was on another compound, it would be carbon 1, most likely, because it has to be the smallest number. But in this case, because there are higher, more important functional groups, that's no longer considered. So we have to satisfy carboxylic acid first. So you number it as such, so that is heptanoic acid. Okay, so once you name the parent, you go for the branches. So you have a 6-methyl and a 4-methyl. Those are easy. Okay, those are just normal methyl branches. But what about the functional groups? They too have special names. If you have a carbonyl group, that means a double bond O that forms ketone or aldehydes, they're called oxos. Therefore, that will be a 3-oxo. Alcohol would be hydroxy. So that will be 5-hydroxy. Does that make sense? Alphabetical order, putting this together, you have 5-hydroxyl, 4,6-dimethyl, 3-oxo heptanoic acid. You see what I'm talking about? This will be a difficult question because it has multiple functional groups. Personally, I would not put this on the test because I feel like this unit is complicated enough as it is. You don't need this in your life. The reason I put that here is some students are curious. They want to know what happens if you have multiple functional groups. Well, they will fight for the highest priority, and then it will be named after that functional group. Okay, so any questions?
I have a question.
Okay.
Isn't it hydroxy? Why is it become hydroxyl?
Yeah, okay, I've seen both, to be honest. Hydroxy, hydroxyl, I don't really distinguish between those two. So I wrote hydroxyl for that one. It just sounds better. I've seen both. You good?
Okay, so it's the same, right?
Same thing, yeah.
Okay, thank you.
All right, cool. Let's move on. All right, so let's go to properties of carboxyl groups. Now, a carboxyl group, the picture is on the left side. You can see that it is composed of a carbonyl group, which is a C double bond O, and a hydroxyl group, which is OH. Okay, but you have to identify this as one single functional group. You can't break them up and call them a carboxyl and a hydroxyl. That's incorrect. It has to be one big thing. Okay, so this is one functional group. The presence of both the carbon double bond O, the carbonyl, versus the hydroxyl, they both contribute to the property. The C double bond O is a polar bond. So this makes a molecule polar. The OH group is also polar, and not only is it polar, it can make hydrogen bonds. Okay, so this molecule is very, very polar. It has a polar carbonyl as well as a hydrogen bonding OH group, meaning that it has very strong intermolecular interactions. As a result, it has relatively high boiling and melting points. So let's do a comparison. In the table on the right, you can see on the first column, it says number of carbons. This compares across different compounds that have the same number of carbons. So let's start with carbon 1, methane, CH4, okay, with nothing else. That has a melting point of -182. That's not a surprise to anybody. It's quite low. methane is a gas. If you look at methanoic acid, still one carbon, all you did was you slapped on the double bond O and the OH. All of a sudden, the melting point becomes 8. Okay, it skyrocketed by more than 100 degrees because of the presence of the carboxyl group. Strong intermolecular forces enable it to become basically a solid at 0 degrees. And at 8 degrees, it begins to melt. Okay? If you look at 2 carbons, ethane, the gas, well, negative 183, not a surprise. Ethanoic acid, you slap on a carboxyl group, all of a sudden it jumps by more than 100 degrees. Again, now at positive 17. So you need 17 degrees Celsius in order for ethanoic acid to melt into a liquid. Otherwise, it will freeze into a solid. I actually have an interesting story about this. I had basically in a giant jar, a jar of pure ethanoic acid I bought for my lab. Okay, it was 99.9%. I stored it in the lab room. And then last winter, the pipes blew. Okay, so there was no heat to my lab. And the lab was still heated by the rest of the building, but it got quite cold. It got to like around 10 degrees Celsius. So I walked into the lab, and why is it so chilly in here? Oh, must have been the pipes. So I take out the ethanoic acid. I'm like, oh crap, it froze completely. I needed the acid to run a lab, and I have in my hand a jar of frozen acid. So I have to thaw that first. I was always just holding it. I was moving it around to a warmer place, holding deadly acid in my hand, just so I could melt some and pour it out to do some lab. So the melting point is 17 degrees. Ethanoic acid will freeze if the temperature drops below that because it has strong intermolecular forces. The one below that, you see oxalic acid. What is oxalic acid? We didn't really learn that, but that's okay. All we care about is that it has 2 carboxyl groups. Okay, if you look at the second column, ethane has no carboxyl groups. Ethanoic acid has 1. Oxalic acid has 2. Having 2 carboxyl groups, the melting point skyrockets to 189 degrees Celsius. It will remain a solid unless you heat it to that temperature. Okay, so you have this in the solid form pretty much all the time. And the same story applies to 4 carbons and 6 carbons. So butane, negative 138. Butanoic acid, well, that will become negative 8. Tartaric acid, basically 4 carbons with 2 carboxyl groups, that goes to 206. And you can see that the melting point will go all the way up. Does that make sense? This means that acids can be found in the solid form. Okay, in grade 10, we tell you that acid must be aqueous. Well, technically, no, you can have a solid acid. All right, so let's move on. How do you make carboxylic acids? Well, remember aldehydes from yesterday, the lesson we didn't have? I hope you watched the video. To make an aldehyde, you must oxidize an alcohol, okay? Specifically, a primary alcohol. If you use an oxidizing agent and you oxidize a primary alcohol, the oxidizing agent will rip away 2 hydrogens, one from the oxygen, one from the carbon with the oxygen, to make water. And then the carbon will be forced to make a double bond with the oxygen, forming an aldehyde. Okay, so that's the first equation there. But if you continue this reaction, if you further oxidize the aldehyde, you will make an acid. How? The oxidizing agent will oxidize the aldehyde by this time donating an oxygen to the carbon instead of ripping away hydrogens. So recall, oxidation refers to the gain of oxygen or the loss of hydrogen. So we're applying the other definition here. So the gain of oxygen. So you will become C double bond O with an OH. So this will be ethanoic acid instead of ethanol. All right, so it's a 2-step process. You can make acids from alcohol, and that seems pretty awesome to me. Basically, what this is saying, you can turn beer into vinegar. Right? I don't know if you want to do that, but it's a possibility if you know what you're doing. This brings us to a very interesting and useful application, the breathalyzer test. So a breathalyzer test basically is a device that measures whether you have alcohol in your breath. So if you're drinking and driving, which you absolutely should not be, and the officer pulls you over, and if you've been driving in an S shape, that's very suspicious, the officer might pull you over and ask you to blow into this device. How would that work? Well, the breathalyzer test relies on the oxidation of alcohol. What will happen is ethanol, that would be what you're drinking, well, that's the only drinkable alcohol. If that mixes with the chromium 6+ ions found in the detector, it will change color, okay? Because the chromium 6+ ions, they're orange. If you didn't drink, you blow, you wouldn't have any alcohol, the chromium 6+ would stay orange and you're clean, you can go. But if you have been drinking, your breath will contain ethanol, and you blow into this breathalyzer, well, that would oxidize and it will become acetic acid. As a result, the chromium 6+, it will be reduced to chromium 3+, which has a green color. So this detection of green will tell the police that you've been drinking. And I believe you get your license suspended for like a month or something. And yeah, and you have some demerit points and you might be fined. So that's just not a good idea. I wouldn't recommend drinking and driving for any reason. If you did drink, well, you guys are too young, but in the future, if you did drink for 6 hours, you shouldn't drive because you would have alcohol in your blood. And despite popular notion, nothing you can do can reduce that. Okay, drinking tea, drinking coffee, brushing your teeth, none of that works. Okay? You will still be drunk. The only thing that will reduce alcohol in your blood is an enzyme called alcohol dehydrogenase. That's the only thing. Okay, that will slowly break down the OH in your blood, and then you will become sober. Nothing else works. So please don't drink and drive. All right, so example 4. Write the equation representing the two chemical reactions that result in the formation of butanoic acid from an alcohol. So the question wants the structure of the alcohol that is all right. So the first step, you have to realize that this is making butanoic acid, which has 4 carbons. Right? You cannot change the number of carbons because the oxidation of an alcohol doesn't change the carbons. So that means your alcohol must also have 4 carbons. Now the question becomes, where do you draw the OH? Since you're making an acid, you have to come from an aldehyde, and you must make that aldehyde. And the only way to make an aldehyde is to have a primary acid. So the only eligible alcohol would be butan 1-ol. It has to be on carbon 1. If you oxidize this, you will make butanal, the aldehyde version of butane. And of course, it will make water because the oxidizing agent will take 2 hydrogens and become water. All right, and you have to continue to oxidize the butanal. Now, plus more oxygen, and you will oxidize this into butanoic acid. Right, so this is what I'm looking for. So any questions as to what happened right here? All right, excellent. This concludes our section on acids. So let's bring our attention to esters. Now, we were supposed to do an ester lab. I had planned this lab, but unfortunately school got shut down, so we're not able to do this lab. This is quite an interesting lab because esters produce a variety of odors that are supposed to smell good. Okay, that depends on your preference, but they're supposed to smell good to most people. Some of these allegedly smells like fruits. I've smelled them, and it barely resembles fruit to me. But I've been told that they're supposed to resemble the smell of bananas and pineapples. And a lot of artificial flavors rely on esters to mimic the flavor of actual fruits. And because they smell so good, a lot of perfumes add esters to produce their good smell. And I don't find perfumes good smelling at all. They actually make me cough. But a lot of people find them, I guess, attractive. So esters, what are esters? They are organic compounds with a carbon with a double bond, so a carbonyl group, bonded to another oxygen. And they separate the long carbon chain into two sections. All right, so on the left, you have a carbon chain denoted by R. In the middle, you have a carbon double bond O with another oxygen, which is bonded to another carbon chain. Okay, that is an ester. Okay. To name esters, it's kind of weird because, again, just like ethers, it separates the carbon chain into two. Recall ethers, well, we learned in a previous lesson, it is just an oxygen that separates the carbon chain, right? So technically, if you just look at this picture right here, that looks like a carbonyl group with an ether. Okay, but that's not how you look at this. This, as a whole, is the ester functional group. You cannot separate a functional group into its components. So here's what you do. You have to identify the two alkyl groups. Okay, the one on the left side of the oxygen, the one on the right side of the oxygen. Well, which one is which is very important. So now you determine the group that is originated from the carboxylic acid, and the other group is originated from the alcohol. So, by the way, an ester is created from the synthesis of carboxylic acid and alcohol. Okay, so one side will come from the acid, the other side will come from the alcohol. Well, which is which? The side with the carbonyl group would be the acid side, and the side with the oxygen would be the hydroxyl side. Okay, and you would have to identify on this one, well, that's a propyl, that's an ethyl. Okay, and that would be the carbonyl side on the left with the double bond O, and the hydroxyl side with the oxygen. So once you determine that, then comes the naming. The carbonyl side, the one with the double bond O, you have to change the ending and add the suffix -ate. Because it's 3 carbons, that will become propanoate. Okay? On the hydroxyl side, you change nothing. That's exactly how it's presented. It's just ethyl. The hydroxyl group will go first, and the OH will go last. So you will arrange it like this. So this is simply ethyl propanoate. Okay, notice that there is a space between the ethyl and the propanoate. This is one of the few examples where you have a space in your name. Okay, make sure you have that space. So do we have any questions regarding how to name esters? It is not the length of the carbon chain that matters. It is where you find the double bond O and where you find the O. All right, so let's do these 2 examples. I will give you a minute. These are very simple examples. It doesn't even have a branch. So I will quickly take this up in a minute. Okay, so you have these 2 questions here. The one on top, all you have to do is figure out which side is the alcohol side, which side is the acid side. On the left, you have an ethyl. On the right, well, that will be your acid side with the double bond O. So you name that butanoate for 4 carbons. Just put them together, ethyl butanoate. You're done. Okay, that one is very straightforward. The one on the bottom, the left side has 5 carbons, so pentyl. The right side has 2 carbon, but that's the acid side. And so that would be ethanoate. And if you put them together, that would be pentyl ethanoate. I believe this is the smell of pineapples. If you actually have this compound and you actually make that in the lab and you sniff it, it's supposed to smell like that pineapple flavor that you get from the artificial flavor. I have smelled this, and it does kind of smell like pineapples, but it smells like perfume, mostly to me. These two are a lot more difficult. Well, let's do this together. So the one on top, you have a benzene ring. That's what makes it difficult. So anyone have an idea of how you can possibly name that one? Anybody? Okay, no takers. You will do this as you would for any other normal question. First of all, the thing on the left. We just learned that the acid version of this will be benzoic acid. So therefore, the ester version will be benzoate. And the right side would have 3 carbons. That would be propyl. Okay, see how this works? And you simply put them together. That will be propyl benzoate. That's it. The trick is to recognize that the benzoic acid is on the left side. Okay, you just name it benzoate. That's the only difficult part. The propyl is very trivial. The one on the bottom, it is hard because it has additional branches. And so what do you do when you have branches? Well, now you have to number the carbons. Notice that we haven't been numbering the carbons because there was no need to. Now you have to. It's a no-brainer to start from the functional group. Okay, the double bond O has to be carbon 1. You go to the left all the way to 4. And you number the carbon on the other branch as well. Again, you start from the carbon with the oxygen and you go to the right side. You have 5 carbons there. So that will be butanoate on the left, pentyl on the right. What do you do with the branches? Well, they're both on carbon 2 and they're methyl, so that's a 2-methyl and that's a 2-methyl. Okay, now here is where it gets kind of weird. You have to put them together. And you have to separate the 2 branches because they're found on 2 separate carbon chains. You can't combine them. So instead, you would have 2-methylpentyl, 2-methyl butanoate. All right, notice that the 2-methyl, one of them goes with the pentyl because it's found on the pentyl, and the other 2-methyl goes on the butanoate. And it's separated by a space. There is a space because esters have a space for some reason. So do you have any questions? All right, that's it. We're good? All right, so that's enough about naming of esters. So let's actually look at the properties of esters. Esters are quite similar to carboxylic acid. If you just look at the picture on the bottom, you can see that on the left, you have a carboxylic acid, C double bond O with OH. Well, an ester is just C double bond O with an O that doesn't have an H. It has another carbon chain. Okay, so that's why we're learning these together in the same class. Carboxylic acids can make hydrogen bonds because of the OH. But esters, they don't have an OH, so they're unable to make hydrogen bonds, but they are polar. It's just that compared to a carboxylic acid, it is less polar. Okay, that means it has weaker intermolecular forces compared to an acid, but still it has stronger intermolecular force compared to a non-polar substance. And also compared to carboxylic acid, it is less soluble in water because it lacks the ability to do hydrogen bonding with the water. Okay. And also, same thing with the melting and boiling point, lower than the acids because you lost the ability to do hydrogen bonding. In addition, esters are not acids. Okay, why not? They're so similar to carboxylic acid, so why aren't they acids? Recall in grade 11, the definition of an acid is the ability to release hydrogen ions in solution. And if you have a carboxylic acid, that's exactly what it does. It will release the hydrogen from the OH in solution and will become just O-. But esters are unable to do that because the oxygen doesn't really have a hydrogen to release. So as a result, esters are not acidic because they lack an OH group. How would you make that? Well, to make an ester, you need an alcohol and an acid, and you need to perform an esterification reaction or a condensation reaction. The esterification is just a very specific type of condensation reaction. In a condensation reaction, you take two things. It doesn't have to be alcohol or carboxylic acid. It could be to anything. Condensation refers to losing water. So you basically rip off H2O from those two compounds, and then they will join together with water as a side product. Hence, you condense the water. That's where it gets the name from. So in the esterification example, methanol, the alcohol with one carbon, will bond with ethanoic acid, the acid with two carbons. Methanol will lose the H from the OH. Ethanoic acid will lose the OH entirely, and they will together make the water, and the oxygen from the alcohol would bond with the carbon with the double bond O on the acid to form an ether, and that will be methyl ethanoate. Okay, that's the reaction here. And in the equation below, you have the formula version of this. CH3OH, that denotes methanol. CH3COOH, that is ethanoic acid. I just want to point out that this is written out in the organic form, meaning that it tells you what the structure is. If you just write this down normally, you would write ethanoic acid as C2H4O2. Right, that's the grade 10 level of writing this. And because I prefer the CH3COOH much better, because it tells you the structure, it tells you the carboxyl group, I prefer that one. I always write it like that. So I've had questions in grade 10, wait, what is that thing? And why did you separate the carbons and the oxygen? I had to explain, well, that's the structure. I prefer this one because, it's very clear. I suggest you also write it like this because there are isomers and you don't want to get confused as to, wait, what is that? If you see a COOH, that's got to be a carboxylic acid, okay? On the right side of the equation, you will have a COO in the middle of two CH3s. The COO denotes ester. If you ever see COO, you have to know that this is referring to the carbon double bonded with an oxygen, and that same carbon single bonded with another oxygen, and that oxygen is single bonded to the carbon that comes after. That is just a shorthand way of representing the structure. Okay, that's the actual official way to represent the structure if you want to write it in a chemical formula. So make sure you can recognize this as an ester. And of course, water is also produced. So in summary, an acid plus an alcohol will produce an ester and water. And that was supposed to be the lab that we'd be doing in this unit. It's a very cool lab because alcohol smells like alcohol, and to some people that smells really bad. Acid smells like, acid, and to, I want to say everybody, that smells very bad. So two very terrible smells, when you combine them, actually produces a pleasant smell because esters are supposed to smell nice. Okay, you were supposed to perform that lab. I have like 99% alcohol with 99% acid, both of which smells absolutely disgusting. You were supposed to mix them. And afterward, you smell, the reward is the pleasant smell. Now, if you screw up the lab, then it will still smell bad. Right, so there's going to be bad smells, but if you actually do it right, it will be pleasant. But too bad we are unable to run that lab. You can just imagine that you're doing this. This can, of course, occur in reverse. If you take an ester and you treat it with an acid or a base, the reverse would occur, and this would be called hydrolysis. Hydrolysis refers to breaking up due to water. The hydro means water, lysis means to break. How would that work? Well, an ester would have an ester linkage between the C double bond O, the oxygen, and another carbon chain. If you add something like sodium hydroxide, which is a base, with the presence of water, this will basically break up your ester so that one of the carbon chains will be attached to the OH, and thus you would have an alcohol with the carbon chain and the OH, and what's left over would be the acid. All right, so that would be a hydrolysis reaction. Okay, that is the extent that you need to know about the reaction of esters. So do we have any questions? Alrighty. All right, so example 7, you have to draw a structural diagram and write the IUPAC name for the ester formed in the reaction between propan-1-ol and benzoic acid. All right, so I'll go ahead and give you around 2 minutes on this one. All right, so for this last example, you have to draw the diagram for the reaction of an alcohol and an acid. Well, you first have to draw the acid. Benzoic acid, we've learned already, just a benzene with a COOH. Propan-1-ol is 3 carbon with the OH on carbon number 1. How you would combine them is that the OH from the acid would disappear, the hydrogen from the alcohol will disappear, and all you have to do is just stick them together. All right, so you have an oxygen from the alcohol sticking to the C double bond O, and you have the structure to the right. Make sure you count the carbons once you draw your ester, because many students make the mistake of having additional or missing a few carbons once you stick them together. Okay, make sure you want to have 3 carbons on the alcohol side. And of course, water is also produced. Make sure you have that as well. So that would be a benzoic acid and propan-1-ol to create propyl benzoate. And this would conclude the lesson. We learn about the carboxyl group, C double bond O with OH, carboxylic acid, how we make them from oxidation of aldehydes, which are derived from the oxidation of alcohols. We learn how to name acid, we learn how to name esters, and we learn about the esterification reaction, where an alcohol and an acid can produce an ester. And we learned some properties of esters. So do we have any questions? All right.